Let me show you how to find the volume of a solid of revolution using the disk method. First of all, what I mean by a solid of revolution is when we take a region and rotate it about an axis. Now, so far, we've been able to find the area of this blue region by using a representative rectangle to help us, but we understand that that rectangle represents all of our rectangles in a Riemann sum. And then from there, we would expand that into the definite integral and find the area of that blue region. But now what we're going to do is to take this region and rotate it around the x-axis. When we do that, we're going to end up with a solid, a three-dimensional shape that is rotated around an axis, so hence the name the solid of revolution. And notice that now what we're going to use instead of a representative rectangle is going to be this representative disk. That representative disk represents all of the disks that we would use to rotate about an axis, and then we'll expand that into the idea of the integral. So what's very important for us is first coming up with some measurements for our representative disk. Now remember, that disk was developed from our representative rectangle. That rectangle had a base of delta x, and its height was f of x. But now, since that representative rectangle sits on top of the x-axis, we're going to rotate that around the x-axis, and we'll create this disk. Now, if we're going to find the volume of a disk, remember, it's the area of the base times the height of that disk. Well, in this case, our base is a circle, so its area would be pi r squared, where the radius of our disk is that f of x. And then the height or the depth of that disk is our delta x. From here, we can estimate the volume by adding up all of these pi f of x squareds, delta x's, adding up all of those individual disks all the way over the interval. And we've seen before that when we let that delta x become infinitesimally small and have infinitely many of these disks in there, that we will get the exact volume in the form of an integral from a to b of pi f of x squared dx. And this will be our formula for the volume of a solid of revolution. So let's say we want to find the volume of the solid formed by rotating the region bound by the x-axis, and f of x is equal to square root of 5x on the interval from 1 to 5. So here I have it graphed, and here is our representative rectangle. We're going to take the region and rotate it around the x-axis. When we do that, everything will mirror itself below and will rotate like this. And this would be our representative disk. Right? The height of this disk is delta x, and the radius here is f of x, which is square root 5x. Now remember, the volume of a disk is going to be pi r squared times the height. This is going to turn into our definite integral. The volume for the entire region is going to be the definite integral from 1 to 5 of pi, and when we square the square root, we'll have 5x, and delta x turns to dx. Now we just have to evaluate it. Using the power rule, x is going to go up to the squared power, and that 5 pi gets divided by 2. And we'll evaluate this from 1 to 5. And we'll have that total volume being 60 pi units. Let's try one more. Find the volume of the solid formed by rotating the region bound by the x-axis and y equals secant of x on the interval from 0 to pi over 3. Now I've graphed half a wavelength of the secant function. It normally goes from negative pi over 2 to positive pi over 2, but we just want to look at the interval from 0 to pi over 3, which is right here. So I draw in my representative rectangle, create my representative disk. The depth of that disk is delta x, and the radius of that is going to be secant of x. We remember that volume is going to be the integral over the entire interval from 0 to pi over 3 of pi r squared dx, where our radius is secant of x. That works out pretty nice for us, because when we square secant of x, our integral really looks like this. We're going from 0 to pi over 3 of pi times secant squared of x dx. And the integral of secant squared is tangent. So I got pi times tangent x evaluated from 0 to pi over 3. So we'll plug in pi over 3 and subtract what we get when we plug in 0. Well, tangent of 0 is 0, and tangent of pi over 3 is square root of 3. So our volume is going to be pi times the square root of 3. And that's how you find the volume of a solid revolution.